Yeah. But remember, in order to be qualified, you have to be first an applicant and satisfy one of those two criteria. Dog's mad. All right. Good. All right. I posted. I know she's. Let me see. I've done how enter. She is wild. All right. Oh, that's what I was talking about last day. So yesterday I was feeling so good. I'm like, oh yeah, we've got a review tomorrow, no big deal. We'll just go through the practice test. And then for some reason, it wasn't until this morning that I was like, crap, I gotta make a practice test. So my apologies, it's posted now. Mea culpa. So anyways, my bad. But it's posted now and we'll go through it together. So, so that's good. I posted it in week 9 because that's where we are today. And I'll bring it up. So make sure if you don't have access to it right now, just make sure that you can see it. Create new note, import. Yeah, well, I had this dog before Jenna Marbles got Kermit, so I know we all want Jenna to come back, but like original Jenna Marbles. Yeah. All right. Yeah, Sermit. Hey, where did it go? There it is. So we'll go through this one. Sermon, yeah. You have to feed your sermon lots and lots of chicken. So I posted the practice test. So we're gonna finish up our notes from last day, and then we'll go through the practice test together, and then I'll post those. I went through it, and it took me 45 minutes to do it. So you will want to keep your pace up. This one is a little bit longer than what I'm gonna make you do on Monday, but I wanted you to have, you know, practice problems for all the different things I could throw your way. So only slightly shorter for the real thing. Ain't no thing but a chicken wing. Math 139. All right. So last day we were converting between the smallest amount of log questions. The logs I put on there aren't that bad. I don't think, but we'll see. Oh yeah, so from last day, we were converting, we wanted to write 42 in base 3. Remember, we were converting between bases, and I think we just did base 2. Okay. Yeah, we were gonna do base 3 and base 4. So let's do base 3 first and then base 4. Fun. Going between the bases. So we had two options, right? We could either use a table of values and just kind of break down 42 break it down into its respective base 3, or we can use repeated division. I actually prefer the repeated division after I've kind of tried both, but it's up to you. So we can use a table. Oops. Use a table or repeated division. So I'll do them side by side. You do not need to do both. Pick one, stick with it, right? Really figure out how it works. And what I want you to do, and I'll bring it up when we do the practice test as well, once you've converted your bases, you're obviously gonna go online and find some base converter and make sure that you did it right, right? Yeah, good. So I want you to make sure you just check your work. You're gonna have to be working fast, so you won't have that much time to check your work. But you got to check your work, right? So there's no reason to submit something that's wrong. But in order to kind of make it happen in the amount of time that you have, you'll need to know what you're doing. So that's my goal, at least. All right, so 42, what we can do is we can rewrite 42, and we want to work in base 3. So first thing I'm going to do, actually, if I'm using a table, is I have to kind of write out 3 powers of 3. So 3, of course, to the power of 1 is 3, 3 to the power of 2 is 9, 3 to the power of 3 is 27, 3 to the power of 4, use a calculator, is 81. Okay. 42 would go somewhere in here, right? 42. So what you need to do is you need to figure out how many times can you fit 27 into 42. Only once, right? So what this looks like is you're going to write 42 is 1 times 3 to the power of 3 plus, so 27, so 42 minus 27 is 15. Okay? Yeah, you always have to show all your work for these questions. And it's usually quite a bit of work, so don't skimp out. Okay, so we've dealt with 27 of these 42. So now we have to go to the 15. So now you move the 15 over here. And so you have 15 is, and as a multiple of a power of 3, right, 15, you can get 3 to the power of 2, right, 9, into 15 just once. 1 times 3 to the power of 2 plus 9 plus 6 make 15. This 6 is the next one we have to deal with. And what we're trying to do, right, if we start at 3 to the power of 3, we went down to 3 to the power of 2, so that's good. So now I have to move to 3 to the power of 1. It looks like it's working out. And so, so the 1 comes from that only goes to the value, yeah, exactly. So I think in the next example, it's going to go in more than once. So we're going to see it where it goes in more than once. Or even in the next number. But at 6, it's kind of hard to tell. So 6 is going to be 2 times 3 to the power of 1 plus 0. We still need to deal with the 3 to the power of 0. But if it's 0, if we've got this kind of essentially a remainder of 0, 0 is 0 times 3 to the power of 0. Okay. Because we have to span from 3 to the power of 3 all the way down to 0, or even negatives if we have to deal with negatives. We're not going to do that, but for this problem. Okay, so now this is our number in base 3. So therefore, 42 base 10 is understood, is the same as 1120 base 3. One thing you can kind of check yourself with, if you're working in base 3, you know you only have 3 symbols to work with, 0, 1, 2, right? And so you only have 3 digits that you could go for, right? And so the highest multiple that you could pull out is 2, and then it would go out to 3, and then it would cycle over, right? And so, so if you're working in base 3, just remember you only have 3 symbols that you could work with. So if this way makes sense to you, that's great. Like I was saying, repeated division kind of clicks for me a little bit better. Just depends on what you like, I guess. So what you do for repeated division is you start kind of down low, leave yourself lots of space up above, because you're going to start doing your division, working your way up. Okay, so what I'll do is I'll put it kind of here, 42, and then I'm going to divide 3 into it. So I'm going to set it up just like as if I'm doing some sort of long division. It's not really, but sort of quick long division. Right? What we find is that 3 goes into 42, so just do 42 divided by 3. I get an even number, or a whole number, I should say, of 14. So then the remainder is 0. Okay. From 14, I divide into 14, 3 again. So 14 divided by 3, I'm not at a whole number anymore, but I'm going to put my whole number here, right? Because if I do 14 divided by 3, I get 4.66666. And so my whole value is 4, and then I have 4 times 3, so that's 12. Is there a potential max number of lines to leave out? Like for moving up this way? Is that what you mean? A max? No, but I mean, half a page, if you suspect that there's going to be lots of divisions, should be enough. Right? So here I just kind of left 1, 2, 3, 4, 5, 6-ish lines. So 3 times 4 is 12, so I've got a remainder of 2. Not surprisingly, we've already done it, but you only have to do one of these, right? So that's okay. Hey, how come it's all kind of shifted? Been writing sloppy. So now if I put 3 into 4, well, 3 goes into 4 one time with a remainder of 1. And 3 goes into 1 0 times with a remainder of 1, this one here. Why do I collapse all these? I should have stacked them nice and proper. Instead, they're all... Okay, so now, right, reading from top to bottom, this is our answer. So therefore, 42 is 1120 base 3. Yeah, I think this way is easier. And they said you can't go sightseeing. What do they know? So here, right, I think this way is easier because you don't actually need to establish, yeah. It's all, I don't know why it's all falling over. Teresa. That's good. It's really good. Here you kind of have to do some work and figure out what your powers of 3 are, whereas that's not really necessary here. You just kind of go for it, right? Let's do another one. What if we write here? Write 42 in base 4. So we can use a table. Use a table or repeated division. Whichever one you like. Oops. What would happen if I used the wrong color? Okay, so if we're using a table, then we need to establish powers of 4. So 4 to the 1, I'm not going to care about, but 4 to the power of 2, of course, is 16. 4 to the power of 2, 16. 4 to the power of 3 is 64. So here I'm kind of tapped out because 42 is somewhere between here and here, right? 16 and 64, but there's quite a bit of distance here. But working in base 4, I have 4 symbols to choose from. So I can have more than 1 or 2, or I can have up to 3 multiples of 16 in a number that I can extract. So what this looks like is I have 42 and I'm going to divide out 16, or 4 to the power of 2. So if I have 42 divided by 16, I get 2 of them, 2.625 of them. So 2 times 4 to the power of 2 plus, so 2 times 16 is 32. So I have a leftover of 10. Okay. So now I have to deal with that 10. And because I've dealt with the 4 to the power of 2, my next option is just extracting as many 4 to the power of 1s as I can. And what that looks like is I get 2 times 4 to the power of 1. 2 times 4 is 8, so I have 2 left over. 2 I have to deal with. I have to deal with this too, but I also know I have to keep going because I'm not at 4 to the power of 0 yet, right? I have to cover all my powers. So this is going to be 2 times 4 to the power of 0. Remember, anything to the power of 0 is 1, right? So 2 times 1 is 2, so then you're done. So therefore, 42 is 2, 2, 2, base 4. That's a cute little number, isn't it? 42 is 2, 2, 2, 2, base 4. Cute. Yeah, so if you're using the table values, then you have to span 4 to the power of 2, 4 to the power of 1, and then once you hit 4 to the power of 0. Even if this was a 0 here, you would still represent 0 as 0 times 4 to the power of 0, right? Yes, exactly. So that's the situation that happened here, where we had 0, but we still had to talk about, okay, well, what is it times 3 to the power of 0? It just happened to be nothing. Okay, repeated division. I'm going to try to keep it nice and clean this time. 42, writing bigger than I ever have. So now I'm working in base 4, so I'm dividing in 4. So 42 divided by, I did 2. 42 divided by 4 puts me at 10.5. So up above here, nice try, Emily. 10 with a remainder of 2. Okay. Then I move on to the next one. So 10 gets divided by 4. 10 divided by 4 puts me at 2.5. So a whole number of 2, but 2 times 4 is 8. So I have a remainder of 2. Okay. Then if I try to divide 4 into 2, I can get no 4s out of 2, but this is where you stop for the repeated division, right? When you have a 0 here, and then whatever's underneath here is your remainder. So therefore, again, 42 is 2 base 4. Yeah. So we've got a couple of more base conversions in the practice test. So what we'll do is we'll go through the practice test together, and then we can kind of slow down, hopefully, for those conversions. Right. Any questions though before we do? Start with the practice test. Okay. So, practice. I'm calling it test 2. It got too confusing. Quiz 1, little fun quiz 1, little fun quiz 4. Wait, what happened to the other ones? Well, they've been around. So anyways, I'm just, we'll call it test 2. We'll kind of fix it later. So you've got this practice test. Like I said, it's a little bit longer. Quiz test 1. Yeah, you got me. No, it's a test. Quiz test. So yeah, 2.0. Super easy, fun test. Yeah. All right, so let's talk about, we'll go back to question 1 first. Okay. You'll see, oh, maybe I'll make a separate file for the solutions. How about that? Practice 4, test 2, solutions. Because then I can post them separately. Okay. Super easy, fun test. Okay, so it's been a while, and this is actually, I'm trying to make it as easy as possible. And like I said, I promised I went through the final exams that I have, the previous final exams, and this is how far they took the 1-to-1 and ON2 or specifically ON2. So that's why we're going to keep it nice and simple like this. We didn't really talk about codomain and range, so that's why I'm bringing it up now. because I saw it on the final and I want you guys to be prepared. So we'll talk about it now. We talked about it before, but we didn't emphasize it. Okay, so we have sets A and B, and then we define some functions from A to B. So F is this little guy and G is this little guy. Okay, if you find it helpful, then you can draw kind of 1, 2, 3, 4. You've got A, and then you've got B, A, B, C, D. I don't actually find it that helpful, so. And then for F, you can map 1 goes to C, 2 goes to A, 3 goes to D, and 4 goes to C, right? So that's what it's saying. I don't actually love this because it's all crisscrossy and whatever. So I'm just gonna blab it out, okay? So what we have to do is we have to figure out if F, the function F, is 1-to-1 and or onto or neither, right? There, it could be the case that it's neither, and you have to explain. So out here in the margins, you've got the number of marks available. Typically I work on a 2-mark scale or kind of a 1, you know, you sort of got it, you're almost there, just missing some quick little things, and then of course you got it right. So my marking scheme is not that elaborate. So for A, F is going to be, so we want to know if it's 1-to-1 first. So if it's 1-to-1, it means that each input only maps to one output. And so 1 maps to C and 4 maps to C. That's bad news for the 1-to-1, right? So we say F is not 1-to-1. F is not 1-to-1. And you have to explain, since both 1 and 4, so both the inputs 1 and 4 map to C. Since both the inputs 1 and 4 map to C. Okay. So that's how I want you to check it. If an input maps to an individual output, then that's 1-to-1. And it's onto, and I know I had a hard time with this, but what we're going to say is that it's onto if each element in the output is mapped to. Okay, so in this case, we map to C, we map to A, we map to D, but we don't map to B, so it's not onto. So F is not onto, since B is not mapped to in the set B. Okay. Notice that the following functions from A to B, right? So we're mapping from A to B. So B is the, it's called the codomain. For B, G, well, so 1 maps to D, 2 maps to C, 3 maps to B, and 4 maps to A. So it looks like nothing is kind of tangled or overlapping. And so it looks like it's going to be 1-to-1, and it is. So G is 1-to-1. And we'll say, since all inputs map to unique outputs, by the same kind of idea that we had here, okay, well, if it's onto, then it maps to every element in B. So A is mapped to, B is mapped to, C is mapped to, and D is mapped to. Yeah, so you could use a horizontal line test as well. So kind of looking at it this way, horizontal line test, it can only cross a curve once horizontally to be one-to-one. Probably easier to use if you have a function, like an actual function. But yeah, it definitely works. So G is one-to-one, okay, and G is onto, since each element in B, since each element in B is mapped to or onto if you want. You know what? I will say onto. Why not? If it helps. What is the codomain of F? I'm just going to tell you what it is and tell you why that is, and then the difference between the codomain and the range. So C, the codomain, since F and G map from A to B, B is the codomain for each of these, right? B is the set of possible outcomes, not necessarily the actual outcomes, so which is the range. So B is the codomain for both F and G. That's not really what the question was asking, but I wanted to establish what it is, just so you have it, right, to reference during the test. And then D, the range. So what's the range of G? Well, the range of G is all the possible outputs, so all the outputs that we actually get. For G, we get A, B, C, D, which is the codomain A, B, C, D, which is B, right? For F, our range is A, C, C, D, right? So A, C, D would be the range for F. Range is the actual outputs. So range of F is the set A, C, D, and the range of G is, well, I'll just say B because I'm running out of room and I want to keep this question on one page. Okay. For when you're organizing your work, when you're submitting it to Gradescope, I'll just let you guys know right now, I'm just going to make one question, so like one picture, I guess, per question. Of course, each question can span multiple pages, but in Gradescope, it's just going to be kind of per question, so not per part, just per question. So I don't know if that helps. But anyways, we'll see. Gradescope is weird. Well, it's handy for me. Keep them all in the same place. 0.5, 0.7 question. well, then you'll have to let me know. Yeah, this is math. Yeah, let me know which ones that's for now later. Maybe send me an email or text me. All right, so that's question 1. Let's move on to question 2. Okay. Doesn't need to be that big. Okay. If f of x is x squared minus 3x plus 2, here's your favorite algebra exercise, and g of x is the root of x minus 1, then yeah, it's easiest if you only submit one PDF on Gradescope, and then just kind of make sure you know where the questions are and you tell it where the questions are. Yeah. So we're going to find f plus g, we're going to find g minus f, we're going to find f composed with g and g composed with f. So I kept the functions pretty easy, I think. No fractions or anything, so it's good. PDF, SAM, basic. Oh, nice. So A, if we have to do f plus g of x, well, we know, oops, I'm composing already, f of x plus g of x, right? Notice that each of these are only 1 mark. Some of them are harder than others, but I've kept them just kind of easy breezy single markers. And so f of x is x squared minus 3x plus 2 plus g of x, x minus root of x minus 1. Okay. So there's nothing really I can do here to simplify this, so I'm just going to leave it. Okay. For b, I want to find g minus f of x. That's g of x minus f of x. G of x is the root of x minus 1 minus, and then make sure your f of x is all in brackets. Okay. The root, or sorry, minus x squared minus 3x plus 2. And then, of course, to simplify this, I'm just going to bring this negative inside. But there's not much else I can do. Root of x minus 1 minus x squared plus 3x minus 2. Moving on to our compositions. If I have to compose, so f composed with g, wherever I see an x, I have to put in g of x. So f composed with g of x is f of g of x. Okay. F of x is x squared minus 3x plus 2. So I have g of x squared minus 3x, which is 3 times g of x plus 2. Being careful, right, because g of x is going to get replaced with the square root of x minus 1. So you have the root of x minus 1 squared minus 3 times the root of x minus 1, and then plus 2. The root and the square are going to cancel. So you have x minus 1 minus 3 root x minus 1 plus 2. I can simplify minus 1 plus 2, but that's about it. So I get x plus 1 minus 3 root x minus 1. And how you arrange those is kind of up to you, but I would just leave it like that. I think it doesn't need to be fancy. Yeah. How about g composed with f of x? well, that's g of f of x. That's the root of f of x minus 1. Which is going to be the root of x squared minus 3x plus 2 minus 1, all under the square root. I can simplify this a little bit, but not a lot. X squared minus 3x plus 2 minus 1. Why do I have minus 1 here? Plus 1. Find mistakes in my solutions. Unless I screwed something else up. No. 2 minus 1 is 1. Feeling confident. Nice. Okay. So, these ones I think are pretty breezy, as long as you've got your algebra kind of, oh, can you bump? Good? Okay. As long as you've got kind of a decent handle on your algebra, I'm not gonna make these super difficult, but, you know, a little bit tricky. Yeah. So let's go to the next question. Question 3. So now I'm saying f of x is going to be 2x plus 1 over 3, right? I'm not going to be nasty and have an x down here. That makes a real mess, right? Oh, why didn't we take 2a further? You want to go further, huh? Nah. Then I'd have to do something with this little guy. That's a no thank you for me. Well, do you see anything that you want to do? I don't know. No, I don't. Yeah. She had me. Well, I'm sorry, Ashley. We just stop here. There's nothing else I can do. Or easily, I mean, I can maybe factor something here, but because of the square root, so x minus 1 is stuck under the square root, there's nothing really I want to do here, so just throw your hands up. It's close enough. Yeah. All right. All right, so first thing we're gonna do, we've got this function, we're gonna show that it's 1-to-1. I don't know if you remember, we show f of a is equal to f of b, means that a equals b. And then we're gonna find the inverse, and then we're gonna show that the inverse we found is indeed the inverse with the cancellation properties, right? Kind of assumes we know the cancellation properties, but I mean, I'll tell you what they are here. Maybe you already know. So first thing we want to know is if it is 1-to-1. Hint, hint, it is. You just need to show that it is, right? And so f of a, if we set it equal to f of b, is going to be 2a plus 1 over 3, forcing it to be equal to 2b plus 1 over 3. And what we need to show is that this means that a equals b. Here it's pretty obvious, and that's why I chose it. we're not going to do crazy math here, but first thing I'm going to do is I'm going to move this 3 over here so that I need to multiply both sides by 3. 2a plus 1 over 3 is 2b plus 1. You can really go lots of different directions here, but you're going to be multiplying by 3 either way. So the 3 divided by 3 is going to cancel. So now I have 2a plus 1. 2a plus 1 minus 1 is 2b, right? If I subtract 1 from both sides, kind of shoving everything over to the left-hand side, now I have 2a is 1 plus 1 minus 1, so 2a equals 2b. Bing, bing. Hey, black. Whoa, where did that come from? I never use the black pen. 2a is 2b. So now, of course, we see it. A is 2b divided by 2, which is going to cancel 2 over 2. So A is equal to B. Okay. Therefore, and I want a concluding statement, right? Because the question says, show that f of x is 1 to 1, and therefore invertible. I'm kind of giving you a leg up here. Right? It has to be 1 to 1 in order for us to be able to find the inverse. So I need to say, okay, this thing is 1 to 1, and if you really want to show off, then tell me it's invertible because it's 1 to 1. So therefore, f of x is 1 to 1 and invertible. Right. B, we're going to find the inverse of f of x. So what I'm going to do, because it's way up on the screen, 2x, I'm going to write f of x is 2x plus 1 divided by 3, and we want to find the inverse. I think I gave you a couple of options, right? You could either write, well, either way, you start by writing y equals f of x, where y is 2x plus 1 over 3. I mean, way more steps than you need to. You can just start here, y equals 2x plus 1 over 3. And then you can solve for x and then swap your x's and y's. I actually like to swap x and y's immediately and then solve for y. So we get x, oh, new page here. So x is 2y plus 1 over 3. Yeah. Solving for y, I need to multiply 3 over here. Oops. So I get 3x is 2y plus 1. And then I need to subtract 1. Whoops. 3x minus 1 is 2y. And then I need to divide that all by 2. And then I do a little revolving door because I like to have my y's on the left, whatever I'm solving for on the left, but I get y is 3x minus 1 divided by 2, which is now going to be my inverse. Okay. So we have the inverse, feeling pretty good about it, right? One way we can check it, well, I even force you to check your work. Show that the inverse you found is indeed the inverse of f of x using the cancellation properties. So now we have to show that, okay, f composed with the inverse is equal to x, and the inverse composed with f is also equal to x. Both of those have to be true in order for this thing to actually be the inverse. So for C, we need to show that f composed with the inverse is equal to x, and the inverse composed with the function is equal to x. are so, this is such a small function that we can probably do them side by side to save some space here. So we're not scrolling so much. But what I'm going to do, I'm going to do f of f inverse of x, which is, okay, remind myself what f of x is, 2x plus 1 over 3. So I have 2 f inverse of x plus 1 over 3. In place of the inverse, I'm going to put 3x minus 1 over 2. So I get 2 times 3x minus 1 over 2 plus 1 divided by 3. Things are just going to cancel out, right? And this one's going to move a lot quicker than the ones we were doing in class with the proper fractions. So 2 over 2 is going to cancel out. So what I have next, you won't believe what happens next. 3x minus 1 plus 1 over 3. Minus 1 plus 1 goes away. And I guess I could skip another step, but I won't. 3x over 3, but of course 3 over 3 goes to 1. So I'm on the right track here. If you found your inverse correctly and you did your math correctly here, you will end up with x here, right? And so now what I'm going to do is I'm going to do the other cancellation property on this side. So f inverse composed with the function, which is going to be, okay, the inverse is 3 times f of x minus 1 over 2. Okay. Where f of x, so 3 times f of x, which is 2x plus 1 over 3 minus 1 over 2. Same sort of mechanics here, right? 3 is going to cancel with 3, so I'm left with 2x plus 1 minus 1 over 2. Plus 1 minus 1 goes away, so I have 2x over 2, which of course is just x. And then I'd love to see a conclusion. Therefore, f inverse of x is equal to 3x minus 1 over 2 is indeed the inverse of f of x equal to 2x plus 1 over 3. This doesn't look like -1. Okay. Good. So that's kind of the end of the functions section. Well, we will deal with functions always, but moving on to our favorite logs, log laws. Bob, blah, blah's log. So like I said, especially for these, I just wanted you to have log Doug Dimmadome. No, I don't know Doug Dimmadome. So here, I gave you 2 of each, right? Likely what's going to happen is I'll give you one to expand and one to simplify. But I just wanted you to have some practice. So, and maybe I'll keep it at 2, I don't know. Seems like a good length. So if we have to expand this thing as far as possible, right, we have to use the log laws. And so if we're multiplying inside the logs, we can expand them by adding logs. And if we're dividing inside here, then we're subtracting logs. Okay. So if we have the log of 7x squared y to the 5th, that's going to be the log of 7 plus the log of x squared plus the log of y to the 5th. Okay. I can take it one step further, right? I can bring this power downstairs, and that'll expand it even more. Right, and so what I have is I have the log, I'll try to write nicer here, log of 7 plus 2 times the log of x plus 5 times the log of y. And then you're done. There's nothing more you can do. Natural log, of course, is just a special case, the log base e. So the natural log of x to the 4th over 2y to the 3. What I'm going to do is, it doesn't really matter which order you do this here, but there's x to the 4th over 2y to the 3. So I'm going to break up this division first by subtracting 2 logs. So I get the log of x to the 4th minus the log of 2y to the 3. Okay. I see a lot of things here, but I can bring this 4 down in front. What if you kept 7x up here, do you mean? Yeah. Well, it's 7x squared, and you want to expand it as far as you can, right? So you want to break them up if you can. So here, there's a couple of things I can do, right? I can bring this 4 down in front, but I can also deal with this one, which has multiplication inside, right? And so now I'm adding, making sure you keep this negative out front here. So there's a couple of things going to happen here. 4 times the log of x minus the log of 2 plus the log of y to the power of 3. Okay. I can bring this negative inside, right? Minus log 2 minus log of y to the 3, but this log of y to the 3, I'm going to rewrite as 3 log y to really expand this thing out. So I get 4 log x minus log 2 minus 3 log y. I've dropped the brackets, but I can put them on. You don't need to have the brackets, it's just nice. It's a nice to have. Okay. How about contracting these things or making them as small as possible? So now we're going to work kind of backwards from what we just did, right? And just making use of those log laws that we know. So here, 2 log x, oops, I can rewrite, just working backwards from what we just did, right? Here we were bringing the powers downstairs. Now I'm going to bring these powers back up to try to collect these things. And so what I get in A is, I'm going to write it out, 2 log of x minus 3 log of y plus 4 log of z is the same as the, and I'll say log, but I mean the natural log in this case, log of x to the 2 minus the log of y to the 3 plus the log of z to the 4. Right? All of these have the same base, log base e, and so I'm able to combine these, right? So I have subtraction, so log of x to the 2 minus log of y to the 3, and then plus log of z to the 4. It doesn't actually matter the order that you do these, but I would probably smush these together and then put them in the divisor, right? So what am I going to get here? The log of x to the 2 minus the log of y to the 3 z to the 4. Kind of smushing in accordion style from the right hand side. So then I have this, the log of x to the 2 over y to the 3 z to the 4. And now, once it's a single log and there's nothing I can simplify in here, then I'm done. Shouldn't the z be on top? I put it on the bottom. Why did I put it on the bottom? It is on the top. The way I did it, I would have had to pull out a common negative. Delete. No harm, no foul. Yeah, what happened here? I should have pulled out a common negative if I wanted to do that. And then I would have y to the 3 over z to the 4. And then I'd have a fraction over fraction, which would just put the z to the 4 on top, ultimately. Anyways, but the log of let's see here, x squared, oops, z to the 4th, oops, minus the log of y to the 3. There. Combine those first. And then I have the log of x squared z to the 4th over y to the 3. And that's what I actually have. Well, in my solution, I just skipped straight to here, which would be totally fine if you skipped this step and went straight to here. But if you just did what I did previously and you screwed this up, I could still give you part marks. Started and got x and z on the top. Yeah, so you should have x and z on the top. You did it right. I did it wrong. But now it's right. And that's what matters. How about we do B? So now I've got the natural log of x squared minus 4 minus the natural log of x minus 2. All right. So this one's a little bit sneaky, as you'll see. So you'll want to keep your wits about you. But what you get is the natural log. You can combine these because they have the same base, and I'm subtracting. So I get the natural log of x squared minus 4 over x minus 2. The sneaky part is you think you're done, but x squared minus 4 you can actually factor out. So something simple like this, we should be able to recognize. So the log of x plus 2 times x minus 2 over x minus 2. If you find that you are ending up with something that kind of looks like you could pull out a common factor of x minus 2, for example, try it, right? Usually it's going to factor out and you're going to be able to cancel and get something even more simplified, right? So if it feels like, well, going against what I just said, no, you're done. For something like this where I ask you to simplify, well, if it's just one step, there's probably more to it. So here, and you can double check, right? X squared minus 2x plus 2x, so those go away, and then minus 4, x squared minus 4. Right? Because I don't know about you guys, factoring for me is not that fun. I hate it. But we have to do it for these reasons, they cancel out. So we get the natural log of x plus 2 is the simplification. Yeah, I actually just covered polynomial long division in class today. It's been a long division heavy week for me. We do polynomial long division in pre-calc. Factor and remainder theorem. It's actually pretty fun, pretty soothing. Just like changing bases. Yeah, soothing. How about question 6? Here, I gave you a lot, of course. Probably a few more than we needed, but it's nice to have lots of practice. Just sweating like crazy through the tests. Well, yeah, if you're in your onesie. So here, we're going to solve for x and simplify as far as possible and give the exact solution. I want the exact solution. Log of x over 2. No, you should get log of x plus 2. Kermit. Okay. Or maybe you've moved on to the next question, question 6. I don't know. All right, so we're going to solve for x. So we've got kind of increasing difficulty, I would say, right? If we have 216 to the x equals 36, well, the whole reason we use logs is so that we can bring x's down in front. There are actually a couple of ways that you could solve this. Just make sure that you end up at the same solution that I do. I'll just use one way. You could use log base 216 on either side, right? Or I just like to use a natural log. If I ever have to bring something down from the power, I just throw a natural log around it and then use the log laws. So we have a few options for solving this. Right, just so you don't think you're wrong. The first option would be to take the log base 216 of 216 to the power of x equals whatever you do to one side, you have to do to the other side. Okay. Log base 216 of 216 to the power of x is saying, well, what? It's going to cancel out to x. I have a hard time with the what to the power of what? 216 to the power of what is going to make 216 to the power of x? X is, right? And so x is going to be log base 216 of 36. But if we're trying to calculate this, this is really hard, right? Especially if you are working on a very basic calculator, but you'd have to use the change of base formula. So for the change of base formula, I like to use the natural log. I always gravitate towards the natural log, but you can use any log, log base 10, log base e. So x is going to be the natural log of 36 over the natural log of 216. And if you try it on your calculator, oh yeah. Oh yeah, x log base 216 of 216, yeah, is x times 1, exactly. I skipped all that step. Here, I'll write it in here. X times the log of 216 of 216 is x times 1. I got carried away. Shh, there are no baddies. She's just barking at random stuff now. So x is going to be the natural log, or the log of 36 over 216. This is the change of base formula, right? And so, but and I don't expect you to get there, but if you do, if you try it on your calculator, the natural log of 36 over the natural log of 216, it's just 2 over 3. If you stopped here, I'm totally fine with that, right? You can stop here, but I'll just do, which is 2 over 3. Can stop here. Okay. Just happens to be. So that's your first option. Your second option for solving this thing is my preferred way, because it's just how I always bring stuff down from the power. So if I have 216 to the power of x is equal to 36, I just take the natural log of both sides. Now, this x comes down in front, right? Yeah, so x would be 2 over 3. So I get x times the natural log of 216 is the natural log of 36, which if I'm solving for x is the natural log of 36 over the natural log of 216. I am going to run check on the dog and probably throw her outside. Keep working A through F, BRB. Let's continue. Okay, so like I said, two options to arrive at basically the same thing. I don't expect you to go to 2 over 3 from here, so I'm just going to leave it. Where's B? E to the negative 2x is equal to 450. So because I've got E, I'm definitely going to use the natural log, but also because it's my go-to for bringing stuff down in the power. So I've got the natural log of e to the negative 2x, but I have to do it to both sides, right? That would be probably the most common mistake, is you forget to do it on the one side. You do it on one side and then you forget to do it on the right-hand side. So you get negative 2x times the log of e, which is just 1. So if you wanted to start writing this as negative 2x right away, that's totally fine. Is the log of 450. So negative 2x is the log of 450. And so x is going to be the log of 450 divided by negative 2x. If you wanted to bring that negative up top, that's fine. I would just leave it like that. Hey, no x. It stayed. Negative 2. Got carried away. How about C? Let's see. Yeah, okay. Making sure I've got it in my notes. Log of x plus the log of x plus 1 is equal to the log of 20. Now the log is of course log base 10, so you could use your calculator if you wanted to. But you have an x here and an x here. I think the easiest thing to do would be to combine these logs. Again, you have a few different ways that you could go about it. You could move this log 20 over here, right? Or you could make sure that you've got log base 10 of something on the left-hand side equals log base 10 of something on the right-hand side, and then use that cancellation property that, well, if you have a log of A is equal to the log of B, then A must be equal to B. Right, and so what we can do is we'll find that the log of x times x plus 1 is equal to the log of 20. From here, because of that cancellation property, right, the same base something law, log base 10, log base 10, therefore x times x plus 1 must be equal to 20. So x times x plus 1 must be equal to 20. I'm trying to solve for x though. So this looks ripe for a quadratic, right? If I expand this out. And so I get x squared plus x minus 20 is 0 if I move this 20 over here. So now I'm just dealing with no logs anymore, right? So they're gone. So now we've got x squared plus x minus 20. I'm going to use the quadratic formula. I always use the quadratic formula to factor quadratics. Why not? So just remember, you've got negative b, or sorry, x equals, let's highlight that, x equals negative b plus minus the square root of b squared minus 4ac over 2a. We don't even need to factor it actually because it's equal to 0. So a is 1, b is 1, and c is negative 20. So a is 1, b is 1, and c is negative 20. So then what we can say is that x is negative 1 plus minus the square root of 1 squared minus 4 times 1 times negative 20. All over 2 times 1. So x is going to be negative 1 plus minus 1 plus 80 is 81. Nice perfect square. So we've got the root of 81, taking it nice and slow here. Negative 1 plus minus 9 over 2 puts me at either negative 1 plus 9, so that's 8 over 2, and x is equal to negative 1 minus 9, so negative 10 divided by 2. So x is 4, and x is negative 5. Cuidado! Can we take the log of a negative number? No, je suis désolé. We've got log x here, log of x plus 1, whatever we say our solution is. Has to be a solution to the original equation, which was up here, log x. And so we can't take the log of a negative number. Since we can't take the log of a negative number, x equals 4 is the only solution. So x equals 4. Womp womp. Okay. All right. D. Okay. Just want to check it out. I've got the natural log of e to the 3 minus the natural log of x is equal to 2. Okay. One thing that's kind of a psych here is this is just 3. The natural log of e to the 3, if you think about it, it's just 3 times the natural log of e, which is 1. So 3 times 1 is 3. Mwah, right? But we have to know that. So 3 minus the log of x is equal to 2. So what we can do is we can say, well, this is the same as 3 minus the log of x is equal to 2. If I bring this 3, so I'm still solving for x, so I have the negative natural log, sorry, I've been calling it the log. The negative natural log of x is 2 minus 3, which is going to be negative 1. So that means that the natural log of x is equal to 1. If I'm trying to shake out this x, I have to raise it to the power of e, right? Log is the natural log is log base e. So I have to raise e to the natural log of x. That's how I'm going to cancel it out, is e to the power of 1. So x is e to the power of 1. Or just e if you want. E. Feeling confident that I've got it here. Log base 10 of 10 to the x. Same scenario, right? Minus 2 is equal to log base 10, which I shouldn't write, of 100. Okay. So this here, again, is just going to be x times 1, right? But we've got x of the log of 10. Just deciding if I want, well, my writing isn't cooperating. The log of 10, but also, should I write it? Should I just write 1? I'll keep it. Minus 2, log base 10 of 100. I think you had one of those on your assignment, right, where it says, okay, well, log base 10, so 10 to the power of what equals 100? 10 to the power of 2 equals 100. So log base 10 of 100 is 2, right? And so you can replace that with 2. Now I'm just being inconsistent. Not doing it here, but doing it here. That's okay. So x minus 2 is equal to 2. So x is 2 plus 2, which is 4. F. Wowie mama. the log of the natural log of the log of x is equal to 0. Solve for x. Just need to undo it. So here we go. The log of the natural log of the log of x, closing all my brackets, 1, 2, 3. You guys know about closing brackets. Is equal to 0. Okay. So just picking away at this, I'm going to raise it to the power of 10. Log base 10, I'm going to raise everything to the power of 10, and that's going to chip away at this first log. But I have to do it on the right-hand side as well, right? So I have to play along on the right-hand side. So I get 10 to the power of log base, the log of the log of the log of x. Close, close, close. Oh. 10 to the 0. Keeping in mind that anything to the power of 0 is just 1, right? And so how I think of this as happening, it's not really, well, it is. The 10 and the log base 10 are going to cancel, right? That's the reason I raised it to the power of 10. So now I have the natural log of the log of x is 1, right? 10 to the power of 0 is 1. You can check it on your calculator. To cancel this natural log, I have to raise it to the power of e, but I have to do it on both sides. So I get e to the natural log of the log of x is e to the power of 1. That chips away at that one. So now I have the log of x is e. So now I just need to raise this to the power of 10. So 10 to the power of the log of x is 10 to the power of e. So x is 10 to the power of e. A little bit tricky, right? But you just need to keep chipping away at it. Okay. Ready for some logic? Yeah, so because I want the exact numbers, so I want the exact solution. So E is just like pi, it's a constant. And so, so you just keep it as E. Yeah, for the exact solution. Nice. Oh, here, e to the power of 1, I'm just writing e. Is that what you mean? Yeah. Cool. But then, yeah, just keep it as e for the exact solution. Good. Okay. Logic time. Yeah, you could leave it as 10 to the power of e to the power of 1. Anything to the power of 1 is just itself though, right? But technically, yeah. Go for it. All right. Remember these? So first thing we're gonna do, so we have 14 to the power of 1. Oh no, I better pick it up a notch, huh? I'll pick it up to the power of 2. Pick it up, pick it up. So if we have to translate this into symbolic form, first I need to establish my symbols, right? And so notice that this first part is worth 2 marks because you have to do this correctly. And then each of the rest are just worth 1 mark each. Just, did you do it, did you not do it? Or not did you do it, did you not do it? Did you sort of do it, or did you do it? Okay, so what I'm gonna do is I'm gonna first establish, so if you brush your teeth with Smiles toothpaste, then you will not have any cavities, okay? So I'm gonna establish my statements first. You brush your teeth with Smiles toothpaste. You will not have any cavities, but that's the negation, right? So it depends on how you wanna think about it. I'm just gonna establish it as you will not have any cavities as not Q. So what we're gonna do is we're gonna let P be the statement, because we're used to P's and Q's. So I'm just gonna keep it to P's and Q's. P be the statement, you brush your teeth with Smiles toothpaste. And then what I'm gonna do is I'm gonna recognize that this is the negation, and then I'm just gonna use it as not Q, is you will not have any cavities. If you wanted to talk about Q, you could say you will have cavities, right? But because our converse, inverse, and contrapositive are going to be in terms of the not Q, I'm just keeping it as not Q. So A, we have to translate this statement into symbolic form. And so if P, then not Q is what we've got here. So if P, then not Q. Notice that, right, the actual work for A is not bad, but you have to establish these, your P and not Q, or however you want to say it. B, put it on a fresh page here. Oh, you know what I want to do? I wanted to keep them on separate pages. I need to do it now before it's too late. There. Nothing ever happened. B, I want to write the converse. Might be handy to have the converse, the inverse, and the contrapositive, what they mean handy, right? And so the converse is going to be not Q, then, so if not Q, then P. If you do not have cavities, then you brush your teeth with Smiles toothpaste. If you do not have cavities, then you brush, I'm going to shorten it a little bit, with Smiles. Because I'm running low on time. Inverse. The inverse of this thing, if you have it handy, is not P, then not Q. Okay, which we've got a double negative here. So what I'm going to do is I'm going to say, so not P, then Q. Is what I can write. Not P, if you do not brush with Smiles, then you will have cavities. If you do not brush with Smiles, then you will have cavities. the contrapositive of our statement would be not Q, then not P. So that's the same as Q, then not P. If you have cavities, then you did not brush with smiles. If you have cavities, then you did not brush with Smiles. Smiles toothpaste. Or you do not, I guess. Doesn't matter. I'm sure there's a past tense, present tense thing going on here, but we'll ignore that. Okay. 8. A truth table. Oh yeah, well, I always post my notes on Moodle after class, right after, so yeah, you'll have these. What I'm wondering though is, would you rather work through the truth table or the change of base question together? And then I'll post the rest of the solutions because we're running low on time. Truth table, change of base. One vote for truth table, truth table, truth table, truth table. That was my vote. Let's do it. Truth table. And then I'll post the solutions to the other ones so you can work through them. All right. So use a truth table to determine whether this statement, so the negation of P or Q, if and only if not P and not Q is a tautology. Remember, a tautology is where you end up with all truth. And if it is, how can you rewrite it? Just as a heads up, right? Logical equivalence is if you have an if and only if statement that is a tautology, right? So it's kind of foreshadowing, nudging in the right direction. So let's use a truth table here, P and Q. We're gonna set it up like we always do. Make sure you leave yourself lots of space here. True, true, false, false, true, false, true, false. Always set it up like this, right? Always start here. True, true, false, false, true, false, true, false. This makes sure you has all your combinations. You have all your combinations. I'm going to deal with P or Q first. So P or Q. Well, as long as one of them is true, the whole thing is true. So we've got true, 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 false. Okay. The negation of that, not P or Q, is false, 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 true. Dealing with not P and not Q separately and then putting them together. Not P is false, false, true, true. Not Q is false, true, false, true. So then putting these things together, so not P and not Q, not P and not Q, and I'll kind of throw some brackets around just to make sure they don't run into each other. So false and false, well, that's false. False and true is false. True and false is false. And true is the only way that you could get a true for and. So false, 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 true. Okay. If and only if, it's going to be true if you're going from the same truth value back and forth, right? So it's a false bouncing to a false, a true bouncing to a true. Both of those would yield true values for this back and forth arrow. Now I'm going to cheat and I'm going to do this. Oops. And just do my arrow up top here because I ran out of room. It was too lofty. Okay. From this side, so that's here. Actually, here's what we'll do. Call this A and this B. How about that? Yeah, you can do that. False goes to false. That's true. A false if and only if false. That's a true statement. Again, false going back and forth between false, that's true. False to false is true. True to true is true. So because we have all trues here, this is a tautology. This statement is a tautology. Since this kind of, if it was all false, would it still be a tautology? No, I think tautology only refers to true. But I'm actually not 100% sure. We just only deal with true, this, but it's a tautology. Since the implication is a tautology, we can replace it with the double arrow, which is logical equivalence. So what that's saying is not P or Q is logically equivalent to not P and not Q. This is actually De Morgan's laws, but we're not going to call it that. Not here, not now. It replaces true, true with false, false. Too perfect. Okay, so what I'll do, because I know I've run out of time, is I'll post the rest of the solutions before I post the notes. So give me just 10 minutes, and I'll whip these up, and then they'll be up on Moodle. If you have any questions when you're studying before the test on Monday, just shoot me a text is probably the easiest thing, or an email is fine too, whichever you prefer, but just let me know and I'll help you out. Any questions before we go? So just to summarize the test, I'll post it as a PDF. It'll be available at the start of class on Monday. I'll be in Zoom if you have any questions, just like last time. But you don't have to be here. It's just if you have a question during the test. Okay. Feeling good? Awesome. All right. Bye, guys. Enjoy your studying.